workshop. Um, um, just let me know when you've invited everybody to the session, and I can begin.
Yep, everyone are in.
Okay. Okay. So for this final session, I wanted to introduce bidirectional transformers, primarily due to its popularity to perform state-of-the-art performance in a lot of NLP tasks, and not just for classification, but it does perform very well in classification tasks. And the great thing with the bidirectional transformers is the architecture yields a very nice flow to allow transfer learning of the model to be applied to different NLP tasks. So for today's agenda, I'll be reviewing LSTM today, kind of getting an understanding of where bidirectional transformers have come into play. By that, before I actually look at bidirectional transformers, there's a couple components we need to look at. One being the attention mechanisms, the third being transformer models, and the fourth is being the actual bidirectional transformer, which is commonly used as BERT for bidirectional encoding representation from transformers. So the learning objective for today, what we want to take a look and try to understand is how to apply attention and transformers to addressing the limitations of LSTM, understanding the actual attention mechanisms. We also want to identify the differences between transformer and LSTM, and then really understand the BERT components. And with that understanding, implement and fine-tune a pre-trained BERT model for our classification task. So just a recap for LSTM. Sorry, I think my slide was a little unfocused. From what we recall, this is the LSTM that we saw before. We have a set of inputs and we feed it to the LSTM in a sequential order. And based off that, we have the output of the LSTM go and perform our classification. Now, an issue with this is trying to understand really what the focus is in our model. So during the classification task, if through the regular standard LSTM model, there isn't really, the model isn't really trying to identify what input to really focus on. It's treating the representation of all the inputs equally to try to predict the classification. However, this is not really the case when we're doing classification and try to understand the sentence. We actually pick on specific keywords to focus on to try to make to analyze our sentence and generate an answer. So the way this is achieved is through an attention mechanism. Now, the way this works is we have our LSTM, and the LSTM generates some hidden representation of the input at that time stamp. So what all those inputs outputs of the LSTM, those hidden representation, go towards this attention mechanism. This attention mechanism tries to understand tries to understand uh, the distributed weight of focus towards each output. So uh, each hidden representation of the input at that time. So with that distributed attention, it tries to calculate this context vector, this right block right here. And it does that by taking the hidden representation, multiplying it by the score for that specific hidden state. So it's trying to multiply the hidden representation to how much it should focus on. And that generates a new hidden value, a new hidden representation with a scaled version based off the attention. This is all those hidden representations are summed together to generate the context, which will be used for the classification. So this is how LSTM is incorporating attention by first trying to identify how much attention each of the outputs of the LSTM should have, and then updating those hidden representation based off that value. Now, the way this attention works is there's multiple approaches to it, but the essential approach is the general approach is to have a feed-forward network that tries to calculate the distribution of it and generate a softmax distribution based off all of the input weights. So in this case, let's assume that our input is only 5. So this attention will generate a softmax vector of dimension 5. So when we multiply it within this context, when we multiply it within the hidden vector, the cumulative score of the attention will be 1. So there's no information that's being lost. We're just scaling each of the hidden outputs of the LSTM in proportion to how much we should focus on it. So there's that. There's another component that I want to introduce was this LSTM in a bidirectional manner. So in the original LSTMs that we saw last week, we were only looking at one direction. We were looking at the input from left to right. So as we feed in one input, the first input, we read in the second input, and that's 4. So when we're trying to calculate the representation of our sentence, that representation is based off of the word representation at that current time is trying to generate a representation based only on prior words that it saw. However, language model is actually language is actually in terms of bidirectional, where we also there is information associated both from words prior as well as future words to that words. So what we show here is a bidirectional LSTM. And what a bidirectional LSTM does is it looks at both forward and backward directions. So in the forward direction, it's the general left to right, but in the backwards model, we generate right to left. So the input gets fed in reverse order at the LSTM and generates and we look at the output at the first instance as compared to the forward, where we look at it the instance at the last input. From there, we can concatenate those two representation from the forward and backwards to perform our classification. Now, we're going to see why this is important more in the transformer and why we need bidirectional. Now, let's take a look at the transformer. Now, in the transformer, transformer was first introduced in in uh, a paper released by the Google Brain team. Um, and it was in this article, in this paper, attention is all you need. Now, the main architecture of the transformer is outlined in this diagram. Now, the initial proposal of the transformer was for machine translation. However, we're primarily focusing on classification. So we're actually not going to take a look at all the components of transformer, but just look at the component that's necessary for us in the classification component. So in the transformer model, it can be divided up into two main phases. The first phase is the encoder, which is outlined here in green. The next component is the decoder, which is outlined in red. So the idea of the transformer when it comes to its initial motivation of machine translation is you take your input, so your starting language, your source language, you take its input, encode that encode that sentence within that source language, uh, generates a representation of that source language and feed it to the decoder. What the decoder then does is try to decode it to generate the same sentence but in the target language. So in the case of classification, we actually don't care about the decoder component because we are not translating uh, uh, our input to another set of output language. So if we take a look at the encoder component, uh, it's really two essential networks and a key connection model. So the first one is the attention mechanism, which is of multi-head attention, and we'll have a look at what the attention head, multi-head attention does in a later bit. Then we have the feed-forward network, which is just a two-layer with a ReLU activation. So that's pretty straightforward that we saw before. Now, there is this connection, this add and normalization connection that we have not covered in the prior session. However, this type of connection is of a residual connection. So this type of connection is um, unlike how we saw the feed-forward neural networks before or the standard connections that we saw from LSTM or RNN, where the connections of the network tries to identify a direct mapping from the input to the output. When we have residual connections, what the model is actually trying to find out within its weights is the residual information needed to update the input to the new output. So in terms of the model learning, in the standard approach without residual connection, what the model is trying to learn is the direct output, the mapping to that direct output. What happens when you have a model with residual connections is it's actually trying to learn how to update how to update the input to generate the new output. So, and again, we have two of those residual networks connections because essentially we have two network components, the multi-head attention and the feed forward. Now, look at self-attention first before looking at multi-head attention. So as I mentioned before, what attention is trying to do is trying to identify what to focus on in terms of generating an output. Now, what self-attention does in terms of NLP is it tries to understand how the relationship of each word in the sentence within the sentence itself. So in this example right here, the areas, the words that are highlighted red is the word that we're trying to our base word, and the highlighted words is the words that are related to that red word, where the more opaque that the highlight is, the stronger relation that word has to our base word. So in the first example right here, we have the in this, if we were to train our self-attention model within this context, within this word, um, it would not relate any other word with the, primarily because the is really a stop word, uh, which doesn't really need to have any direct relationship with any other words. Now, in the FBI, we can see that it's actually focusing a lot on the because it is the identifier for the FBI. Now, is having a high correlation with FBI because it's is the FBI is the association of who is referring to. And then chasing, we can actually see that it has strong connections between FBI and is because that sentence has a high correlation with that word being chased. We know that chasing is being associated with FBI. Um, and another component we see that if we look at the very end of the sentence, we see that the focus of this whole sentence is really chasing, criminal, and run. So within this whole representation of this whole sentence, we can see that the whole sentence is really focusing on these three words. Now, we can actually see how self-attention works within this example right here. So if we have the cat stuck out its tongue and licked its owner, we can see that licked, based off this description, has a strong correlation with cat and owner, where cat in relation to licked is the who. So who, the cat is who licked, is doing the licking, and owner is the what. Now, there is a limitation with self-attention in the fact that uh, the context representation is limited to one. In this context, this is a good representation. However, there's actually another representation we can look at, and it's the relative position of the lick in correlation with tongue and licked and its owner. So there's another domain, another set of relational representations that we can have with lick with other words. Now, this is where the multi-head attention comes in, where we try to generate various self-attentions in parallel, uh, generating various level of context with from various relative positions. So in this case, we can actually map both those relationships of licked to cat and owner, as well as focus on the other relationship of licked towards tongue and licked and its. Now we're going to move on to BERT and try to understand why we need BERT to begin with. Why didn't we just stick with LSTM and what we have been doing prior? So the big motivations regarding BERT is really the way we've been doing word representation before, and the fact that we've been basing it off primarily on language model. Now, the problem with language model is it uses context from right or left to calculate its probability distribution. And it needs to do this in order to generate well-formed probability distribution. However, as I mentioned before, the analysis of language isn't actually in a unidirectional manner. It's bidirectional, where given the word, we want to associate it with prior words as well as future words to get to grasp the true understanding of that word in terms of its context. Now, BERT was introduced to solve this model in trying to design a bidirectional model by using masking. Now, the way masking works in the BERT is what it does is it takes its input and masks a certain amount of the input, and that percentage of masking will depend on your specific application, as well as the resources. Now, if you mask low amount of words, then is that will be computationally expensive for training. However, if you mask too little amount of words, then uh, then then it becomes very difficult for the model to learn. So there's a trade-off between performance, computational-wise, and performance of the model. Now, the BERT model, the way its architecture is you give the input with some of the words being masked. It goes through some embedding layer that we saw in prior works before. However, it's slightly different in the fact that it does not just generate the embedding based off the semantic correlation with based off language model. But we'll take a look more in detail of that embedding in the following slide. Now, it goes through that transfer encoder that we saw before, where it goes in and tries to find multiple self-attention relationships amongst these words and generates the output. Then it goes to the classification layer and the softmax layer to generate the output, trying to identify trying to predict what those mask words are. Now, for the embedding layer, it's slightly different in the fact that the embedding consists of multiple components. The first component is the token embeddings. So the token embedding is very similar to what we've been seeing in prior sessions, where it tries to understand the semantic and an embedding representation of the token that has strong semantic representation. Now we have this segment embeddings that looks to identify embeddings of each word in terms of its segmentation association within the whole sentence, as well as the position embeddings that looks to uh, generate a word representation for that word in relation to its position. So the combination of these token, segment, and position allows our BERT model to generate a representation of each word with a representation of each word in its various contexts that it's used. Now I talked about um, how BERT is used to you mask the input and you try to predict those mask output for language model. However, that isn't in the realm of classification really. That's really more of understanding. That's really in the realm of language model, where it's trying to understand the representation of that whole sentence. Now, the way we use BERT for the classification task is we actually apply transfer learning, where we use pre-training for that mask task, the one that I mentioned, to learn the word representations of our vocabulary. Then we take that pre-trained model and we fine-tune it to our specific task. And the way we fine-tune it is we actually keep majority of the components the same. We just take we just adjust the output to be towards our specific task. So in the case of classification, we would take our BERT model and append a classification network at the very end. So in most cases, we'll actually append a multi-layer classification before network to our model. Alternatively, you can use BERT for other tasks, such as the duplicate detection model. Now, in the duplicate detection model, we have two sets of sentence inputs. Now, the great thing with BERT is they design architecture such as a way that it can work off of one sentence input as well as two sentence inputs. And the way it does that is it actually feeds in the input, both input sentences at once, but it delimitates it using a special token, using the separation token. So if you are having a problem such as the duplicate detection problem, where we wanted to see if two questions were the same, the input would be question 1 separated by the special token, and then we'll have question 2 um, appended to it afterwards. And the end classification result would be the binary classification of if those two sentences are duplicate. It also works off of question and answer pairing, where we can feed in the question and the answer as the input, and the model tries to classify if they are valid question and answer pairs. So that is the end for the introduction to the BERT. Are there any questions regarding the overview of the BERT before we move on to the application? Okay. So if there's no questions, I say we take a 10-minute break, and then we reconvene at 6:50 for the application component. Hello, everybody. So I hope everybody is back at this time. So now towards the application component of the session. So in the code example that I provided, we're going to look at applying BERT to the sentiment analysis task that we saw in prior session regarding the movie reviews. So in the first block of code that I have here, this is, again, should be very familiar. This is the exact same code from prior sessions of downloading the data set from the Kaggle and storing it in your Google Drive. Now, this specific command, so the specific package that we're going to use um, comes from the Transformers package, which is available by the Hugging Face Corporation. So they provide a very nice uh, transformer models that's compatible both in PyTorch and TensorFlow. So something similar to Keras, but primarily dedicated to pre-trained transformer models. And the documentations for this package is at huggingface.co slash transformers. So to actually install it, you can install it using a pip. So in Google Colab, the specific library is not pre-installed, so we would have to install it using exclamation mark, and then with the command pip install -qq transformers. And what this will do is it will install the package within this session. Yeah, okay. Actually, before you run anything, it's good to double check that you have GPU. Yep. So we are using an accelerator, so that's good. We would want to use accelerator in this case because the model that we're training on is a large model. So we want to utilize GPU for this instance. And the next line of code is just to link this Google Colab session to the Google Drive to access the data set, as well as save any key results that we want. So I'm going to go ahead and do that. So by connecting to the Google Colab, I can access the data set that I downloaded from the prior session. One thing to note regarding installing packages within Google Colab, it's very similar to access to your Google Drive account, connecting the Google Drive account to your Colab. It's session dependent. So as soon as you terminate this session, uh, the package will be removed. So if you relaunch a new session of this notebook, you would have to re-download uh, the Transformers package. Uh, this line of code is very similar to what we saw in prior work lab and prior sessions, where we will just load in our data sets using pandas, since it is comma delimited data. And just to recap, what our data set looks like is we have a set of sentences which are divided up into phases. So each sentence gets divided up into each phase, hence the phase ID and the sentence ID. And then each phase has an associated labeled sentiment towards it, where um, we have 5 labels: negative, somewhat negative, neutral, somewhat positive, and positive, where negative is 0 and positive gets a value of 4. So like anything that we do, we need to do some pre-processing. Now, the pre-processing that we do, it's very important when you do the pre-processing that you do when using pre-trained models, especially when you're using pre-trained models primarily for feature extractions, like what we will be doing here, where we're using a pre-trained BERT model to uh, to get word embeddings for our words already. So an important thing to do with the pre-processing is to match the pre-processing to the pre-processing that was performed when the initial model was trained that you're loading in. So in this case, we want to load in our important packages. So we're going to load in that package that we just installed, the transformers. And from the transformers, we want to specifically import the BERT model as well as the BERT tokenizer. And what the BERT tokenizer is going to do is handle primarily the majority of our pre-processing, and the BERT model will actually be the model that we use to load in a pre-trained model. We load in our necessary PyTorch because we will be developing the BERT model using the PyTorch component from the transformer rather than the TensorFlow. And we load in a module from the scikit-learn, specifically the train test split, just to split our training data sets into training and validation. And we load in matplot and cyborg just to do some plotting. And specifically this, we are going to load in the pre-trained BERT base model for uncased models. I'll show how we can there are different models, pre-trained BERT models available in the transformers, and we will have a look at those, as well as we'll kind of discuss some key differences regarding the BERT base as well as the BERT large. So we can load that. And the powerful thing regarding using this pre-trained BERT model is the fact that these BERT models has been trained on a large corpus. So these models has been trained on the Wikipedia data sets, which contains 2.5 billion words, as well as the big book corpus dataset, which contains another 800 million words. So the amount of data that it was pre-trained on to generate a rich word embedding representation is large, which we know when it comes to deep learning, a large data set is very powerful. The next set of code is primarily to adjust the matplotlib, just to adjust it from inverse colors as the current editing scheme that I have is in night. So, so we can see the graphs. I just editing the matplotlib to be white. So we can run these. So in reference to the pre-trained models available, so these are all the pre-trained models available. So we have the BERT models, as well as we have other very popular state-of-the-art transformer models. The GPT, which was developed by OpenAI. We have the transformer extra large, as well as the XLNet. This is primarily just being trained on the Wikitext as well as the English model. XML models, Roberta, so a variant to the BERTA models. The still BERT, and so again, variation to the BERT models, CTR generated by Salesforce, Kevin BERT, again, variation, Albert, variation, and T5, and so forth. So we have a lot of available pre-trained models available here. To focus on the actual BERT. So in the actual BERT, we see two variants for each, uncased and case. So again, for the uncased, everything is just trained on the lowercase. Cased is case sensitive. Now there's two variants when it comes to the base and large. So now for the difference between the base and the large is in terms of the architecture. So the BERT base only contains 12 layers with 768 hidden neurons for each layer and 12 heads for the multi-head attention. Now for the BERT large, we have 24 layers, each layer containing 1024 hidden neurons, and this contains 16 multi-head attentions. In both cases, though, they both are trained on using the AtomW optimizer with linear decay for the learning rate. And then for other languages, you can use the base large variants with a different data set being trained on that specific language. So for this, we're just gonna examine how the tokenization works. So we're just going to take some samples from our data set. We'll take the first 5. And to do the pre-processing, we we load in the tokenizer from the BERT model, specific using the from pre-train, and all you have to feed in to that method is the name of the pre-trained model, and that can be located from this documentation. You just have to select one of these shortcut names and feed it in, depending on the specific model you want to load. So in this case, we're going to load in the base uncase. We're going to get that tokenizer, and so that downloads the pre-trained tokenizer, and we can gather some information regarding some models. Specifically, what we want to see is the max model input towards these models. So that is one limitations to BERT. Since all our input is fed in at one time, there is a limit to the length of our input, where it becomes computationally difficult to process larger inputs. So in our case, for the BERT-based uncase, the max input that was used to train this model was 512. Now, to actually do the pre-processing, all we have to do is feed in a list of our text, our input text, to the tokenizer, and that will generate our pre-processing encoded inputs. So what the tokenizer does is generates a dictionary. The first one generates an attention mask. So what the attention mask is just provides a value of 1 if the given word should be paid attention to, or 0 if there's no attention should be provided. So no attention should be provided for padded words. So since we feed in all our inputs at once as a feed forward, all our input needs to be standard size. So we need to make sure our input is of all same dimensions. So we do padding, and we apply the attention mask to identify which tokens are the padded tokens and which are actual words. So in this case, our attention map is actually all 1, since when we did the tokenizer, we did not specify that instance. Now the input IDs, this is the unique ID associated to that specific word. So similar to what we did when we did word embedding session, where we were converting each text into a unique ID. The tokenizer does this for us, since we need to have the same mapping from the text to the unique ID from when it was initially trained. So we generate all these. And then the token type IDs, this isn't as relevant to us right now, as all our input is of single sentence. However, this is more applicable. The token type ID is when you're feeding in 2 sentences, as I mentioned, that the BERT model is able to support. So in the case of duplicate detection, this token type ID will have more relevance. However, in the case of sentiment analysis, for our specific task, it's not relevant, since all our input is only 1 sentence. We don't have a second sentence associated with it. So we can actually convert back our encoded inputs back into the actual text to see what it looks like. So if you notice, given our text, it's the exact same text. However, it got converted to lowercase, as well as it appended um, some special tokens. So in all instances, it appends the CLS special token at the beginning to indicate that this is for classification, tokenization, and we append the separate token to indicate the end of our sentence. Now, if we were to have two sentences as our input, we would have CLS, our first sentence, this special SEP token, and then our second sentence afterwards. So these are two key special tokens that needs to be appended during the pre-processing stage. So again, we can do the pre-processing again with our sample data. However, we can actually provide more parameters to it in the fact that we can specify, adjust the max length during the pre-processing, identify that we want to explicitly add those special tokens that I mentioned. And since we only have one sentence and the token type ID is not of relevance to us, we can set this return token type IDs to false, since we will never use it in our instance. And then we want to have a unified length, so we can do pad to max length equals true, and we can do truncate equals true as well. Return attention map, and we can explicitly specify that we want to return the attention mask equals true. Of course, we want to do this because we are doing padding. So we want to make sure we know which tokens are real words or which ones are padded tokens. And it also provides this option of converting, returning the actual encoding inputs as a tensor already for us to easily feed it into our model or any other PyTorch model for that instance. So if we actually see the results now, we actually see that we have these unique pad tokens appended so that everything is of unified length to a max of 64, as we specified here. Now, in this step, I am just running through the tokenizer and encoding all our input to kind of get a sense of the length of the length distribution of our data sets after tokenization. The model has been trained on 512 max input. However, our review data sets, it wouldn't be that our text, our phrases wouldn't be up to that max length. So we want to adjust it so that we're not doing unnecessary processing, especially when it comes to the padding. So based off of, so this just provides the distribution of our token count. So we see that a token length size of, so our max token is actually 80. However, we actually see that not a lot of our phrases actually reach up to that point. Kind of seems like 40, 45 is a large enough max size to get majority of our phrases to be fully encapsulated. So just to be on the safe side, we can select 64. Nice number when it comes to processing, especially for binary. So we'll use a max length of 64. So we don't have to do the pre-processing all at once and the tokenization. We can actually offload this during our pipeline of PyTorch. Similar to what we saw before, we can define our data set. So in this case, I defined our data sets where I feed in our data frame and our tokenizer, as well as the max length that we want to generate for padding and truncation. So in the initialization, I am just getting our sentiments, converting it to NumPy, and storing it as our input, and converting our, getting our labels, which is in the sentiment column, converting it to NumPy, and saving it for our labels, and saving our tokenizer as well as our max length parameter. Now to retrieve each, this is where I'll do the pre-processing, where I'll get the review, I'll get the label for that specific row, and I'll pre-process our phrase using the tokenizer, using the same parameters that we saw in this example above here, which does the explicitly adding the special tokens, only returning the attention map and converting it to tensor already, as well as doing padding and truncation to be of max length 64. So that's what we do here. And I return everything just as a dictionary, where we have our original text still. That's primarily, we can use that to do visual infection during evaluation. And then we have our input IDs, which will be fed into our model, as well as the attention mask, which will be fed into our model to let the model know which tokens are real words and which are padded. And the labels, I am just converting it to tensor right away, since everything will be it needs to be in tensor, and we're going to push everything to the GPU. We do similar processes that we saw last week. Sorry, I gotta run these actually. Similar process that we saw last week where we split the data into training, validation. Another thing you can actually do is split this from training to validation testing, and then using the validation testing to split again, to split into validation and testing. So you can actually split it up into training, validation, and testing. That's important. The validation is really to identify when training should stop for the model to ensure we're not overfitting during training. And then you can use testing to evaluate the final results of the trained model at the very end. But for this instance, we are just doing the training and validation. Primarily because we can use the testing set that's provided in the data set, do the predictions, and submit that to see our results, how well our model performed. Now we define our review data sets using the trained data sets and generate the data loader, similar to what we saw from other PyTorch codes from the previous session. So the val data sets, data set review, val df, tokenizer. So we're doing the same thing for the validation data sets. And this just calculates how many batches will be generated from the data loader. Now, training for the BERT model using the fine-tuning from the sequence classification. So the transformer package offers this module for sequence classification. So it's a very straightforward method to fine-tune a BERT model for classification. Uh, what we do is we just load that in. This block of code just identifies if CUDA is available. If CUDA is available, we'll use it. If not, we'll stick to CPU. So the way you load in the pre-trained model from the BERT sequence classification is just use the call the module and use the function from pre-train. Provide the name of the pre-trained model. So again, we use the same name that we use in during the tokenization, so that they're matching. And then we have to specify the number of labels that our classification has. So in this case, our sentiment analysis has 5 sentiments, so we have 5 labels. And of course, we're going to move it to the GPU. Now, when you run this code, it should output definition of the model. It provides you a warning here, and the fact that the model were not used when initializing BERT for sequence classification, and that's fine in the fact that the model that we're going to use it as is not the same for the task that it was originally trained on. So it actually outputs as well some details regarding the BERT classification. So it's just the standard BERT. We have the BERT layers with the multi transformer encoders. However, at the very end, so we have the 12 layers of BERT layers for the transformer. Then we have the BERT pooler. Then what's important here is during the class for classification. So it just has a dropout layer with probability of 0.1. So it's during training, it's going to drop neurons with a probability of 10. And we have a simple linear classification layer with 5 neurons for those 5 to generate the 5 label output prediction. So again, for the optimizer, you can actually use the optimizer, the Atom W optimizer. You can load that in from the transformer. However, to keep it consistent, we'll use the same Atom optimizer that we used in prior session. So you can use the same optimizer that was used during pre-training, or you can change it to a different optimizer. In this case, we're using a different one using the standard Atom. And of course, we're using cross entropy loss function since we're doing a classification task. Now, in this line of code, we're actually doing the training. So we loop through a certain amount of epochs. We set our model to train. So that's what this line of code does. Specify that we're doing training. So it unfreezes the weights. Set our running loss to 0. And we enumerate through our batches. We get our inputs and our attention mass and our labels. Push them all to the GPU. Set our optimizer back to 0 grade because the optimizer is a cumulative. It calculates the gradient cumulative, so we got to reset that manually. Then all we have to do is feed in our input as well as our attention map to model to generate the predictions. And we calculate the loss function using the loss function based off the prediction and our true labels. Then we do backwards propagation to update our, to calculate our gradients. And then we do optimizer.step to update the weights. And we keep doing that, and cumulatively, so we do that to cumulatively calculate the loss function, loss at each batch, and then calculate the average loss for during training. After training, we want to evaluate the model, so we convert the model to, we change the mode of the model to eval, so that will freeze the weights. We run the model, which again, similar to the training portions, we get our inputs, push them to GPU, generate our predictions, and calculate our loss. Now, unlike training, since we don't want to do the updatings, we don't want our models to learn based off the validation data sets, we do not do the backwards as well as the optimizer steps. So we don't need to calculate the gradients as well as update the weights during evaluation. So there's that. And then it'll run through the next epoch and so on and so forth. What's is commonly done when training any model is keeping a track of our evaluation scores, our evaluation metrics, and providing a threshold so that if our meaning that our evaluation is no longer getting better, we can stop the training at that instance to prevent overfitting. Alternatively, another approach is running through all cycles of the epoch, saving the evaluation scores of the model, as well as saving the model of the best, saving the model with the best evaluation score at that time. So when everything is done, we can just load in the model that achieved the best evaluation score. So in this case, what we're using is a stock pre-trained model that just appends a dropout layer and a fully connected layer afterwards. Now, you can actually customize the model with fine tune. So what you can have is you can have the BERT model still, and then include any trailing components afterward, downstream components afterward. So in this case, what we're going to do is we're going to have a dropout again, but in this case, we'll add 2 fully connected layers for the classification. So we just have a classification fully connected layer first with 100 neurons, and then we have the fully connected layer for our label output. And we perform a soft max for our classification. So there's that. And then rather than loading in the BERT model for sequential model, we just use BERT model dot from pre-trained. And we create our custom, we create our custom model by calling it from the class, specifying the number of classes, as well as the pre-trained model that we loaded in before. And we push all our custom model to the GPU. And if we see the output of our custom model, we see it's modified to be reflective of our 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 modifications in the downstream components. And again, right here, this is just an example of training the model at one epoch. So I'm not going to run during the training because the BERT model is significantly large, so it takes a significantly more time to train than prior models that we saw thus far, given the number of parameters that needs to learn. A nice exercise that you can do for this specific code is implementing the trainer module from the transformer package. So what that trainer module does, it streamlines this block of code of training and evaluation using this module. So in training arguments, and it'll train and the training data sets and the test data sets, and it'll mimic very similar to this block of code right here, where it runs through a certain amount of epoch, does the training component, and does the evaluation component. So that is the end of the coding component of this session, as well as the end of the session, as well as the end of this workshop. Are there any questions that anybody wants to ask?
Hey, Alex.
Hey.
I just had a quick. This is kind of pertaining to stuff we covered a while back.
Okay.
But basically, because going into this, I didn't have a lot of background into NLP, so I was just looking into like the processes and stuff on my own.
Okay.
And so one of the things I came across, so like we talked about stemming and lemmatization.
Yes.
So I was looking into like when you would use in some cases. So it came across like it's not something that's always used.
No.
But when it is, of course, like lemmatization, it requires a lot more processing because, it's built on like a neural network.
Yeah.
So, and from what I got was that lemmatization increases like at least the precision, right? It's more accurate in going down to the root word. So I was thinking like in today's kind of tools available, is it always, or not always, but is it usually a good idea to go with lemmatization over stemming?
From my experience, the overall performance, so it does generate better performance when it comes to actually getting the root words, but overall performance for the specific task that I'm trying to achieve, I don't find very much benefit from using lemmatization.
Mm-hmm. Okay.
So I typically stick to stemming, primarily from computational efficiency. From the gain that I noticed from lemmatization, isn't worth the extra processing time, I find.
Okay, good. I just wanted to get your opinion on it. Thanks.
Yeah, but definitely, it's there's other way better approaches than applying lemmatization
Mm-hmm.
that yields better performance. So I typically invest on doing those first.
Sorry, would you mind elaborating like which ones you're talking about, like just some examples?
So, so in terms of other examples, would be focusing more on the actual model that I'm using. Maybe looking uh, uh, at fine tuning my stop words.
Oh, okay.
Yeah, so I find those other things to look at yields better reward than actually testing, contemplating between fine tuning the stemming and lemmatization portion.
Okay.
Yeah.
I had another question.
Yeah.
So I was reading up on like, we have the NLTK library, but then we also have Spacey.
Yep.
So what I kind of gathered was that Spacey is a little bit more updated with current methods for a lot of different NLP related tasks. Is that something you've noticed too, or?
I find Spacey. So what I find with Spacey is it's more. I find there's actually less features than NLTK. However, I find Spacey to be more performance-wise better in terms of computation. So I find I tend to use Spacey more if the both
Features
if they
available.
support both functionalities. Yeah,
Okay.
yeah. But I find in terms of the NLP realm, um, I find it's really more towards the comfortability of which one people picked up first. If they picked up
Okay.
NLTK, they primarily stick with NLTK, and then they'll move to Spacey if something's not available, or if they picked up Spacey first, then they primarily stick with Spacey.
Okay. Makes sense. Yeah.
Yeah.
Thanks for the input.
Okay. Any other general questions? If there's no other questions, I think we can wrap up the session as well as the workshop. Any closing remarks you might have, Eunice?
No, just thank you a lot for all these 5 great sessions, and thank you everyone who joined these sessions. As always, I'm gonna send out the last video of this recording as well as the presentation for your future reference. And if there's anything else, just either email me or Alex, and we could discuss it further from here on.
Okay. Yeah. Thank you. Also, I'm thinking of working up a follow-up workshop of this, going to more details of the mathematics towards some of the things we covered, as well as looking at specifically more of the architecture of more state-of-the-art variants of these BERT models, as well as other state-of-the-art models like GPT, as well as looking at other NLP tasks. I'll be sending a separate evaluation to Eunice regarding that. And I would love if anybody can provide their feedback of specifically what topics they would be interested in a follow-up workshop to this.
Yeah, that sounds great. We'll definitely
Okay.
looking forward for that.
Okay. All right. Thank you
All
again,
right, thank
everybody.
you everyone, and have a great week. Bye.